Hello, and I would like to start a conservation of energy problem for this calculus-based physics class that corresponds to a set of lecture notes and slides I've shown before. So what we have here is we have an object that has mass m, slides a distance d down a frictionless incline of angle, and let's go ahead and change that. That should be angle theta. Okay, so this should be angle theta. Okay, that's a Greek letter. While sliding, it contracts a spring of force constant K and additional distance x, bringing the block momentarily to rest. Find the initial separation d between the block and the spring. Okay, so in order to accomplish this problem, we should probably use conservation of energy. If we use Newton's laws, it could be accomplished, but I think it would be a little bit more difficult. So let us have a look at the spring here with the mass and consider the types of energy the objects have initially and also at the end. Okay, so it's an object of mass m, slides down a frictionless incline. Okay, now we're not told that this mass has any kinetic energy, so let's go ahead and let it start at 0. So let's let the initial velocity here equal to 0 meters per second. And let's also assume that the object only has gravitational potential energy. So let's write that down. That that this object only has gravitational potential energy. Okay. And we should also say, because it's at a certain height, and that height's going to decrease. But then we should also say, as the object goes down, that the spring should compress, and the idea is that its final height should be 0, at least 0 in terms of gravitational potential energy. So in other words, set y final equal to 0 meters so that the final gravitational potential energy is 0 joules. Okay. Now, that should make sense. Now, let's also think about what kind of energy the object has in between and then at the end. So I think that here it's all gravitational potential energy initial. During this period of time, it's kinetic energy. But then all that energy, kinetic energy plus whatever gravitational potential, stores itself up in the spring. That is, it's going to be elastic potential energy. You can imagine that the spring compresses, and however much the spring is compressed is the same thing as the initial energy we started with. So that the final amount of energy is only the elastic potential energy. That is the spring potential energy. Okay? So this is basically our conservation of energy equation. Now, we're assuming that there's no friction, so there's no non-conservative forces here. Let's draw a picture of the trajectory of the mass and the distance that it goes. Okay? So let's draw this line to represent the inclined plane. Okay? And then let's do this for, let's do this right here for the direction down. Okay. And then let's have this be the direction across. Okay. And what that means is I should extend this line over just a bit. Okay. This is a sketch, but I'm doing the best I can. So this is theta, the angle of the incline, theta, and this would be a right angle. So I can go to shapes. I'm going to draw a filled square here. That's because this is meant to represent a right angle for a right triangle. Okay, so let's think about what this distance is. So this distance right here is going to be the distance d plus the distance x, because I think when this spring gets compressed, there's a distance x here that it eventually compresses, however much that is. So I think this distance right here will be d plus x, all right, along the hypotenuse. Then we also can note that the distance that the object goes downward, we could call that height h. And we might even want to call that height h initial, or sorry, let's call it y initial, because the y initial goes along with the initial gravitational potential energy. We're setting y final to be 0. That's this point right here when the object is finally all the way down. The horizontal distance it moves is somewhat irrelevant to us. We're not looking at this horizontal distance right here. But we can get a relationship between theta and y initial and d plus x. So I think we can write down the ratio as sine theta. So the sine theta is going to be y initial over d plus x. Now we certainly might need that. Let's go ahead and start writing out the terms for the initial gravitational potential energy and the final spring potential energy. So this should be mg y initial, the initial gravitational potential energy, is equal to 1/2 k x squared, and x is the final spring compression. But y initial is not something that's like given in the problem. We're sort of assuming we know what d is, or we're finding d. We know what m is. We know what theta is. We know what k is, and we know what x is. So m, theta, k, and x presumably are all things we can measure. We can't easily measure y initial, and we can't easily measure d, but we want to find what d is. So this y initial should probably be replaced from this ratio. So from solving this ratio, d plus x times the sine of theta should equal to y initial. Okay, so this term for y initial can get substituted into this expression. So then we have mg times d plus x times sine of theta equal to 1/2 k x squared. Okay, now the problem is a matter of solving this equation for d. So we want to solve for d, okay? And then what that means is we have to isolate d algebraically. Okay, so that's exactly what we're going to do. So I think sine theta and mg are not d. D is only here. So we need to divide by mg and sine theta. And notice that 2 is a denominator. K and x squared can be considered as a numerator because it'd be like kx squared over 1. So let's go ahead and start to set a numerator separate from a denominator. So let's do d plus x, which is what remains on the left-hand side. By dividing by mg sine theta, this should be equal to kx squared over 2 times mg sine theta. Okay, so now finally we want to get d by itself. So we have to subtract x. So then d should equal to kx squared over, let's see, 2mg sine theta minus x. And this should hopefully be our final expression for the answer that we're looking for, because we were looking for d, the initial separation between the spring where it makes contact and the mass. Okay, that concludes this problem. Thank you for your attention. Hope that makes sense. Please smash that like button. Please subscribe to the channel, and I will see you in the next video.